When you flip a switch and a light turns on, what is electricity actually doing inside the wire? It's not magic, it's tiny particles moving in a very specific way. In this segment, we'll break down how electrons flow only when there's a complete circuit, and what voltage really means as a push behind it. And we'll connect that to how power plants use generators and moving magnets. Ready to see it clearly? Start small. Everything is made of atoms. Inside, atoms are positively charged protons and negatively charged electrons, and that charge difference matters for electricity. Electrons aren't all equally stuck. Some sit in outer shells, and an outside force can free them from their orbit, making them available to move. Once electrons are free, electricity is basically their movement. Those negatively charged particles hop from one atom to another through a material. For that movement to happen easily, you need a conductor. A metal wire, like copper, lets electrons travel through it without getting stuck immediately. But electrons can't just wander anywhere. They must have a continuous, unbroken path, a circuit, so the flow can keep going instead of stopping. That's why a switch matters. When the switch is open, the circuit is broken, so electrons can't complete the path and devices stay off. Close the switch and the circuit becomes complete. Now electrons have a full loop through the wire and the device can be powered. Even with a closed circuit, electrons need a push. Voltage is like pressure, analogy, the force that drives electrons through the circuit. So far, we've seen the basics. Atoms have electrons, some become free and they flow through a conductor only when a circuit is complete and the switch is closed. Voltage acts like pressure pushing that flow along, but here's where it gets interesting. Real circuits also have resistance that controls the flow, and we still need to explain where the push comes from in the first place, like at power plants. That's the next piece. Resistance is the restriction of electron flow. It's like narrowing a hallway. Electrons still move, but it's harder, and that changes what the circuit does. In many appliances, resistance is useful. By resisting the electron flow, parts can generate heat or light, like a heating element or a glowing bulb. Now zoom out. Electricity is a secondary energy source converted from primary sources like coal, nuclear, wind, or solar power. At power plants, electricity is typically generated by spinning generators. The generator creates a magnetic field that forces electrons to move through the circuit. Another simple way to say it, moving magnets can push electrons. That motion helps create the conditions for electricity to flow in wires. To power a device, you need three basics: a conductor like a wire, a complete circuit, and enough voltage to push electrons through. One important caveat: we're keeping this at a simple conceptual level. We're not detailing deeper generator physics or giving numbers for voltage or resistance. Electricity is the flow of electrons through a conductor in a completed circuit. A closed switch completes the path, voltage provides the push, and resistance shapes how that flow turns into heat or light. We also kept it intentionally simple. No numbers and no deep dive into how generators' magnetic field works beyond it forces electrons to move. But now when you flip a switch, you know what's happening inside the wire. Pretty cool, right? A magnet can pull a paperclip without even touching it, and that feels like a superpower. So what's really doing the pulling? In this segment on how magnets work, we'll zoom way in, down to atoms, unpaired electrons, and tiny groups called magnetic domains. When enough of those line up, you get an invisible magnetic field with a north pole and south pole. And there's even a link to electricity. Ready? Start with the big idea. Magnets create an invisible magnetic field around them. That field is what reaches out and causes pushes and pulls. That magnetic field isn't magic. It comes from alignment across billions of atoms inside the material. Lots of tiny effects add together. Inside each atom, the spin of unpaired electrons matters. Their spin makes them act like tiny magnets at a microscopic level. Atoms don't act alone. They group into microscopic regions called magnetic domains, where many atomic magnets point the same general direction. In an unmagnetized object, magnetic domains point in many directions, so their effects cancel out. The overall magnetic field stays weak. Magnetize it, and the domains shift into alignment. Now they reinforce each other, creating a stronger combined effect you can actually notice. When enough domains align, the magnet ends up with two ends, a north pole and a south pole. That's how poles form. Those poles control interactions, opposite poles attract, but like poles repel. It's the same rule whether the magnets are big or tiny. So far, we've seen the chain, unpaired electron spin inside atoms forms magnetic domains, and alignment turns those domains into a strong magnetic field with north and south poles. That already explains why magnets can attract or repel without touching. But here's where it gets interesting. Not every object stays magnetized the same way, and heat can mess with the alignment. Then we'll end with the simple electricity connection. So what changes and why? Some materials make this easier. In iron, nickel, or cobalt, many electrons spin in the same direction, so lots of tiny magnets add up. Once aligned, the magnetic field extends beyond the object. That reach is why a magnet can affect things nearby, not just what touches it. That outside field can attract ferromagnetic materials. The magnet's field encourages alignment in the nearby material, so it gets pulled toward the magnet. A permanent magnet keeps its domains aligned even when nothing else is around. The alignment stays, so the magnetic field stays strong over time. A temporary magnet is different. A paperclip can act magnetized only when it's near a stronger magnet, because its domains don't stay aligned. Temperature effect matters too. Heating a magnet can disrupt alignment inside it, so the domains stop pointing together and magnetic properties weaken. One more stated link. Magnetism connects to electricity. A magnetic field is produced whenever an electric charge moves, even though we're not detailing how. Now you can explain the invisible force without hand waving. Magnets work because unpaired electron spin makes atoms act like tiny magnets, and magnetic domains can line up. When they do, you get a magnetic field with a north pole and south pole. So opposite poles attract and like poles repel. The field can reach out and pull ferromagnetic materials, and a paperclip can become a temporary magnet. Heat can disrupt alignment, and moving electric charge produces a magnetic field too. A battery looks like a sealed little brick, but somehow it can push electricity through your device on demand. So what's actually happening inside? In this segment on how batteries work, we'll break it down into three players: the anode, the cathode, and the electrolyte. The weird twist is that electrons travel outside the battery through the circuit, while ions move inside. How can a chemical reaction create that split? At the big picture level, a battery converts stored chemical energy into electrical energy using electrochemical reactions. So a chemical change turns into usable current. Inside every battery are three main parts: the anode, He, the cathode, E+, and the electrolyte separating them so the reaction stays controlled. When you connect a device, the anode starts releasing electrons. That release is called oxidation in this overview description of battery behavior. Those electrons can't shortcut through the battery, so they go out through the external circuit. That moving charge is what powers the device. At the other end, the cathode plus accepts electrons. The seed says it has a higher potential for electrons, pushing flow toward it. Meanwhile, the electrolyte is a chemical medium between electrodes. It allows ions to flow to balance charge, but it blocks electron flow internally. So while electrons move through the external circuit, ions move through the electrolyte inside the battery. That internal ion motion keeps charges from piling up. One more key step: the electrolyte interacts with the anode, initiating a reaction that creates free electrons, which then get routed into the circuit. So far, we've seen the basic loop. Chemical energy drives electrochemical reactions. The anode releases electrons, and the cathode accepts them through the external circuit. Inside, the electrolyte lets ions move while blocking internal electron flow. But here's where it gets interesting. Not all batteries behave the same once their reactants change. Next, we'll cover primary versus secondary batteries, plus what happens during a short circuit and self-discharge. That's the bigger picture. In primary disposable batteries, the chemical reaction isn't easily reversed. As reactants get used up, the battery can't keep supplying electrons. That's why a primary disposable battery dies. Once the needed chemicals are spent, The electrochemical reactions can't continue to provide electrical energy. Secondary rechargeable batteries are different because the reaction can be reversed. You recharge by applying an external electrical current to push things back. With that external electrical current, the anode and cathode are restored toward their original states, so the battery can again drive electrons through a device. A short circuit happens if the anode and cathode plus connect directly, not through a device. Then electrons rush with almost no control. In a short circuit, the reaction happens too fast, which can cause overheating and lead to damage or fire. The battery stops behaving safely. Even sitting unused, a battery can lose charge over time. That's called self-discharge, and this overview doesn't explain the mechanism beyond that fact. Now you can picture a battery as a controlled chemical reaction with two traffic lanes. Electrons go out through the external circuit to power your device, while ions move inside through the electrolyte to keep charge balanced. The anode releases electrons, the cathode accepts them, and the electrolyte blocks internal electron flow. And we're keeping this at the high-level description, like higher potential for electrons being stated but not quantified here.